Tonight, we are looking at a planet that was hiding in plain sight. It belongs to Beta Pictoris, one of the most famous young star systems in the sky, a place already known for its bright disk of dust and its dramatic planetary history. But a new look with the James Webb Space Telescope has revealed that the system still has a secret, a giant world whose light was buried beneath the glare of its star. The discovery is more than a new dot on a catalog. It is a reminder that astronomy is not only about finding objects that are far away. It is about learning how to separate a whisper from a floodlight, and how to reconstruct a planetary system from faint heat, scattered dust, and patterns that only become visible when instruments are sensitive enough. Beta Pictoris is about 63 light-years from Earth in the constellation Pictor. In cosmic terms, that is practically our neighborhood. The star is young, only around 26 million years old, and it is still surrounded by the leftover material from its birth, a broad, tilted disk of gas and dust, swept into shape by gravity and by the planets moving through it. To the human eye, Beta Pictoris looks like an ordinary star. Through a telescope, however, it becomes a laboratory for planetary formation. Its disk is bright because it reflects starlight, and it contains belts, gaps, and clumps that suggest invisible worlds are clearing paths through the debris. Astronomers already knew that Beta Pictoris has planets. 1. Beta Pictoris b is a massive gas giant orbiting at a distance comparable to the outer planets in our own solar system. Another, Beta Pictoris c, is closer in and more difficult to see. Both worlds helped establish that young planetary systems can be dynamic, crowded, and surprisingly unlike the neat diagrams we learn in school. The newly reported planet is especially interesting because it had not been seen directly in the original observations that made Beta Pictoris famous. The star is so bright that its glare overwhelms the much fainter glow of nearby planets. Imagine trying to spot a candle beside a searchlight, while looking from dozens of light-years away. That is the central challenge of direct imaging. Webb approaches the problem in a different way. The telescope observes infrared light, the longer wavelength radiation associated with warmth. A young planet is still cooling from its formation, so it can glow strongly in infrared even when it is almost invisible in ordinary reflected light. But infrared sensitivity alone is not enough. Webb also needs a coronagraph, a carefully designed optical system that blocks the central star while preserving as much of the surrounding scene as possible. Even then, the data contain diffraction patterns, instrumental noise, and stray light. Finding a planet means proving that a faint signal is real, stable, and located where physics says a planet could be. The new world emerged from that demanding analysis. It is a giant planet, and its presence expands our picture of the Beta Pictoris system. Rather than a simple star with one or two companions, the architecture now looks more like a layered story, with worlds occupying different orbits and interacting with the debris left over from the star's birth. A planet like this is not a miniature Earth. It is likely dominated by hydrogen and helium, with deep clouds and an atmosphere shaped by intense youth. The planet may be several times the mass of Jupiter, although its exact properties depend on models of how young planets radiate and how their atmospheres absorb light. That uncertainty is not a weakness. It is part of what makes the observation scientifically useful. Young planets are natural test cases for theories of planetary evolution. If we can measure their brightness, temperature, and atmospheric chemistry, we can compare the observations with models that describe how giant worlds grow inside disks of gas and dust. There are two broad ideas for how gas giants form. In the first, a solid core slowly gathers enough material to pull in a massive envelope of gas. In the second, parts of the disk become unstable and collapse directly under their own gravity. Each mechanism predicts different conditions, different timescales, and different kinds of planetary systems. Beta Pictoris is young enough that the evidence has not been erased by billions of years of erosion and orbital rearrangement. The dust disk is still visible. Resonances may still be sculpting gaps. And the planets are still bright from their formation. Studying this system is like visiting a construction site before the builders have packed away the tools. The hidden planet also helps astronomers understand why some worlds are easy to find and others are not. A planet's detectability depends on its mass, age, temperature, distance from its star, orbital angle, and the wavelength used to observe it. A world can be enormous and still disappear if it lies too close to a bright star in the image. This is why direct imaging is complementary to other discovery methods. The transit method watches for a tiny dip in starlight when a planet crosses in front of its star. Radial velocity measures the star's subtle wobble. Microlensing uses the bending of light. Direct imaging, by contrast, can reveal the planet's own glow and sometimes its atmosphere, but it usually works best for young, massive worlds far from their stars. When these methods are combined, the result is much stronger than any single technique. An orbit measured over time can confirm that a faint point is bound to the star. Infrared colors can estimate temperature. Spectroscopy can search for water vapor, carbon monoxide, methane, and other molecules. Each clue narrows the range of possible stories. The system's dust disk adds another layer. Dust is not merely background decoration. It records collisions between rocks, evaporation near the star, and gravitational disturbances caused by planets. A gap may indicate that a planet has swept its orbit clean. A clump may be trapped in an orbital resonance. A warp may reveal that the entire disk is being tilted by a companion. In Beta Pictoris, these features have been studied for decades, and they have sometimes produced surprises. A young planetary system can change quickly on astronomical timescales. Comets may fall inward. Asteroids may collide. Planetary orbits can migrate as the system settles. The bright disk is a snapshot of a process still in motion. That makes the hidden planet more than an isolated discovery. It is another piece in a gravitational conversation. The planet's orbit may help explain structures in the disk, or it may force astronomers to revise earlier interpretations. Sometimes the most important role of a new world is not what it looks like, but what its presence makes other features mean. Webb's observation also shows why modern astronomy increasingly depends on advanced data processing. The telescope does not simply take a picture and reveal a planet like a circle on a screen. Researchers remove the star's point spread function, compare images taken at different angles or wavelengths, test whether a candidate survives those corrections, and estimate the probability that the signal is an artifact. A convincing detection must pass several checks. The signal should appear consistently in independent exposures. Its brightness should make sense at the observed wavelength. Its position should move in a way consistent with orbital motion, not with a detector defect. And the surrounding structure should match the optical behavior expected from the telescope. This careful process may feel slow compared with the excitement of a headline, but it is how astronomy protects itself from false discoveries. The universe is full of patterns, and instruments are full of imperfections. A planet is accepted not because one image looks persuasive, but because many lines of evidence converge. What happens next? Astronomers will continue tracking the planet's position. The orbit may take years to measure, especially if the world is far from its star. Future observations could reveal seasonal changes, cloud layers, and the chemistry of its atmosphere. Other telescopes may contribute complementary wavelengths, helping create a more complete physical portrait. There is also a broader question. How common are systems like Beta Pictoris? The answer matters because our own solar system may have formed through a similar phase of instability, with giant planets shifting positions while comets and debris were repeatedly scattered. By observing a young system with several massive worlds, scientists can test whether our planetary history was typical or unusually calm. The hidden planet reminds us that a familiar star system can remain scientifically new. Beta Pictoris has been observed for generations, yet better instruments keep changing the inventory. The map was never wrong, it was incomplete. And that is one of the quiet lessons of exploration. Discovery is not always the first time something exists in our knowledge. Sometimes it is the moment an old mystery becomes sharp enough to study. A world can orbit unseen for millions of years, and then, in one careful observation, become part of human history. So when you look up at the night sky, remember that the stars are not points of light with simple stories. Around them are disks, worlds, atmospheres, collisions, and long gravitational dramas. Somewhere beyond the glow of Beta Pictoris, a young giant planet is moving through its orbit, carrying the heat of its birth into the dark. The James Webb Space Telescope did not just find a planet. It showed us how much can remain hidden inside a system we thought we understood. And as the telescope keeps opening the infrared universe, the next revelation may not come from an unknown corner of space. It may be waiting beside a star we have been watching all along.